All right, next up I want to do 403. We'll do that and then we'll go back up to the node above. So find the eigenvalues and eigenvectors for this matrix. So this matrix, we're fortunate because this is a triangular matrix. So we can find the eigenvalues for it really easily. The eigenvalues are we've got lambda is 3 and lambda is -2. But notice -2 has a multiplicity of 2. So let's look at the node. The node says if an eigenvalue has multiplicity m as a root of the characteristic equation, then the eigenspace associated with it will have dimension m or lower. So that means this one over here is going to have dimension 1 or possibly 0. This one over here is going to have dimension 2, 1, or 0. And you can't tell what that dimension is going to be until you actually go through and solve for the eigenvectors. So we need to do two things here. We need to solve for the eigenvectors for this one and solve for the eigenvectors for that one. All right, so first up, let's do lambda 1, which is 3. So we're going to subtract the eigenvectors, the eigenvalues off of the main diagonal. So that's going to give me 0, -5, and -5. And the rest of my matrix is going to stay the same. So that's setting up my matrix, and now I just need to row reduce that. This thing actually would be pretty easy to do, I think. Kind of interesting there, we've got all zeros in that first column. So that means that x is going to wind up being a free variable. Let's put this in. Let's see. I believe I already have this in here. Actually, no I don't. So for, what do we have? 0, 2, -2, 0, 0, -5, 3, 0, 0, 0, -5, 0. All right, that looks right. That looks right. So when I row reduce it, I get this. That's kind of a weird looking matrix. They're always kind of weird looking when they have zeros in the first column. Or maybe that's just me. So anyway, copy it down, and x is a free variable. So what this gives me is x is just x. The top row gives me, this top row here gives me that y equals 0, and this gives me z equals 0. So the eigenvector, see, this is just x times 1, 0, 0. So the eigenvector that goes with 3 is, the basis of the eigenspace is 1, 0, 0. And if we wanted to play around with that, we could. Let's see. I think I have this actual matrix on here. Let me see. I think it's called M3. Yeah. If you take that and you multiply it by, let's do the column vector 1, 0, 0. That should multiply this thing by 3. Sure enough, it does. Okay, let's do the other one. So we're going to subtract that off of the main diagonal. So my main diagonal is going to be 5, 0, 0, and the rest is unchanged. I'm going to augment that with some zeros, and now I'm going to row reduce it. And honestly, I'm not going to use Maple, or I'm not going to use Octave to do this one, because it's actually pretty simple what's going to happen here. You got those zeros on the bottom. The middle row would become 0, 0, 1, 0. And then you can use that 1 to 0 out the top. So that I copied that -2, but that would get zeroed out. And then that top row we could divide by 5. So the first one will be 1, and then 2 divided by 5 is 2/5. And so my solution is going to be, let's see that, what's my, it looks like y is free. So that top row gives me x is equal to negative 2/5 y. Y is equal to y. And what about z? Well, that second row here tells me z equals 0. So it looks like I only get one vector out of this, or I'll only get one linearly independent vector. So let's see, my x, y, z, that factors into negative 2/5, 1, 0 times y, and that is my that's my basis vector. And that is a perfectly good answer to this. So interesting, this had multiplicity 2, but it only gave us a one-dimensional eigenspace. So let's check it on Octave. So on Octave, let's see, M3 I think is what I call this. Yeah, M3. If I take this now and I multiply it by the vector, I'm going to let B be the vector, negative 2/5, 1, 0. If I multiply M times this, it should multiply this vector times negative 2. Why didn't it like that? Oh, I've got a M3 times B. Yeah, so B is that, and that's going to multiply it by negative 2. Now, there's one other thing I want to say before we end this example. I've got the vector written out as negative 2/5, 1, 0, but you don't have to leave it like that. You know, this is a basis of the eigenspace. So if you wanted to, instead of writing this out, you could scale it by any number. So it might make sense to scale by 5 and then write your answer as negative 2, 5, 0. Because when you're dealing with the basis, a multiple is just as good as the original. So you could write your answer as either one of these, and both of them are perfectly fine.